A black hole is a place where gravity has bent space-time so much that light can't get out. In his new book, Black Holes, Dr. Ed Bloomer uses simple language to explain how black holes form, what's inside them, and what would happen if you fell into one. Let's talk about what he says in this video. Falling into a black hole. What happens if I fall into a black hole is one of the most common questions scientists get asked. It's beyond the scope of this article to explain why so many people seem to be really worried about it, but taking it seriously is a great way to learn how black holes work. Let's say you were exploring the universe and got too close to a black hole by chance. In our case, too close means that you can't get into a stable orbit. To stay in orbit, you have to burn energy. You are now in the ISCO, which stands for the Innermost Stable Circular Orbit. Don't worry. The engines on your spaceship are strong and work well. Other things are also going into the black hole, which is a shame. Molecules of gas, a speck of dust, and maybe some people who don't have as good a spaceship as yours. You are now part of the infalling material accretion disk, which isn't as college-y as it sounds. Even though this stuff isn't part of the black hole, it gets hot from friction and sends out electromagnetic radiation as it sinks into it. The mass of what you're spiraling into determines the frequency and strength of the radiation. For example, protostar accretion disks give off infrared radiation, which may not be too bad because the emission isn't very strong. But in black holes, gravity and friction are strong enough to send high-energy X-rays or gamma rays flying at you. Sorry. Because the disk is flat and moves around what you can think of as the black hole's equator, you might try to get above or below it, but you'll be pulled back into space. You haven't even gotten to the weird stuff yet. This is just basic mechanics, but you might already be in trouble. Send a radio signal to the faraway space station where I'm keeping an eye on things as best I can. It's probably time to start calling for help. What am I really able to do? As you get closer to the black hole, the photons climb out of the gravitational well. This causes a large gravitational redshift in the messages you send. The space station is getting different bands than you are. But while I'm busy returning the receivers, you're getting more worried about the effects on the tides of the spaceship. As you get closer to the black hole, the gravitational gradient gets steeper. This means that the gravitational force on parts of the ship that are closer to the black hole is stronger than on parts that are further away. You're starting to stretch, but the material that makes up your spaceship is strong enough to stop it. In the worst cases, though, the pressure of the tides will pull you apart. This is called spaghettification. What does spaghettification mean? In astrophysics, the tides caused by big gravitational fields are called spaghettification. When something falls into a black hole, it gets stretched in the direction of the black hole and compressed in the opposite direction. In practice, the thing could be stretched out like spaghetti to make a long, thin form of its original shape. The curved line in the picture shows a part of the top of the black hole. In the picture on the left, the astronomer's height and width are as expected. As they get closer to the heart of the black hole, they go through some small horizontal compression and vertical stretching. In the right shot, they are closer together, and the way their bodies shrink and stretch is even more shocking. Spaghettification isn't always the case. Because black holes of different masses have different gradients, it's possible to pass through the event horizon without any bad impacts. Again, this doesn't mean that the force of gravity isn't important. It just means that the slope isn't too high. Suppose this is true. Unfortunately, it looks like other things are also going into our black hole. Even though it might seem nice to have company, particles that fall into a black hole do so in a way that causes them to bump into each other. As we've seen, friction makes the accretion disk give off radiation. And because the gravity force is so strong, particles are sped up to speeds close to the speed of light. As a result, very powerful X-rays and other types of radiation are made. The black hole could even send out astronomical jets of ionized matter that are so strong and move so fast that they are called relativistic jets. Since jet rays can travel millions of light years, we should have seen them by now. They are also complicated and don't have clear answers, so we won't spend too much time on them. They are lined up with the axis of spin, while we in the accretion disk are coming at it almost at a right angle. You already have a lot to worry about. So let's just pretend the planes don't exist. Imagine you're falling into a black hole with no jets or accretion disk that is otherwise totally silent. Now comes the fun part. Because of the black hole's mass, space-time itself is bent. In our case, we're interested in something called time dilation, which is another effect of relativity. We will move carefully here because it is a very sensitive issue. But if we want to describe its effects, we need to be careful about how we see things. From different points of view, things will look very different. Assume I'm still at that space station far away from where you asked for help. Due to time dilation, as you get closer to a black hole, you actually start to move slower. I think that time goes by slower for you than it does for me. From what I can tell, your time travel will stop as you get closer to the event horizon. Remember that the wavelengths of your radio messages for help and any other photons you send out are getting longer and longer, making it harder for me to find you. In the meantime, you feel like normal time is going by. Hold on, isn't time time? How can we be experiencing it so differently? Depending on what's going on, time moves at different speeds. This is not a figure of speech. Things move at different speeds in space-time, not just in the 3 dimensions we usually think of as speed, but also in time. We're really feeling the effects because of the unusual situations we've made. But these changes are happening everywhere to different degrees. If everything else was fine, you'd just pass through the event horizon and keep going to the singularity. Fine and simply are important words here, of course. What is happening outside of the black hole while this is happening? I'm sorry, but I've given up trying to reach you, or even get a sound from you. You've gone as far as you can go. From your point of view, there is no outside to reach, because every path goes to the center of the black hole. From my point of view, and as far as I'm concerned, you no longer exist. Because of this, black holes are the end of everything in space and time. When something goes past the event horizon, it stops being in the universe. They can't talk to anyone and can't be heard. Imagine you're an astronomer in a lab next to a very sensitive device that responds to a single photon of any wavelength that comes from beyond the event horizon of a black hole. When it does happen, a loud alert will go off, so you won't miss it. But day after day, year after year, there will be nothing but silence. From what that device can tell, there is nothing there. A complete lack of information. So in summary, don't go near black holes. Thanks for watching this video.